We are going to look at three different ways of finding limits, and they are going to be algebraic methods of finding the limit of a function. The first one is definitely the easiest. It's called substitution. And this is exactly what you've been doing in algebra probably since you were 10 or 11 years old, where you plug in a number for x in this case and you calculate. So for example, if you're asking yourself the question, I have this function, what is this function behaving like around x equals 0? Well, you could write that in the form limit as x approaches 0 of the function. So x squared plus 2x minus 3 over x squared plus 4x minus 5. And the answer to this is not a particularly interesting one. Like I said, we're just substituting. You've been doing this forever. So take a 0, and everywhere you see an x, you can just replace that with a 0. So 0 squared is 0, 2 times 0 is 0, 0 squared is 0, 4 times 0 is 0. You end up with 0 plus 0 minus 3 over 0 plus 0 minus 5, and that's just equal to 3/5. Okay, so you can say the limit of the function as x approaches 0 is 3/5, which is probably not that surprising. This is just the value of the function when x is equal to 0. Okay, so substitution is always your first port of call when you're trying to find a limit. There are some situations when it's not going to be particularly helpful. So for example, what if you wanted to ask the question, what is the limit as x approaches 1 of that function? Well, the problem with this function is if you substitute 1 into it, you'll quickly find that you get a 0 in the denominator. And you know by now that we are not allowed to divide by 0. That is a calculation that is undefined in mathematics. So direct substitution is not going to help us in this case. We can't just substitute 1 into the formula. Instead, we are going to have to use a different method. This method is simplifying the function. So method 2 we're going to call simplification. All right, and if you're looking at this, you might not immediately think that there's much to simplify. However, if we do a little bit of factoring, it'll be more clear. So let's see, if we factor the numerator, we get that. If we factor the denominator, we get that. And now you can see where we're going to be able to do a little bit of simplification, because we have a factor of x minus 1 in both the numerator and the denominator. So you can sort of think that we're canceling that out. And we can say that as long as we are not thinking about when x equals 1, we can approximate this function to this function, which is a nice simple rational function. Notice I said approximate to. These are not exactly the same because this function is not defined when x is equal to 1. Right? Because if x is equal to 1, you get 0 in the denominator. However, this function as it's written right now is defined for x equals 1. So we might want to add a little disclaimer here. So once we get to this point here, this might not seem very helpful because we have this function, but then it says, well, this is not the function when x is equal to 1. So you might be thinking, how does that help us? Because we want to know what is the limit as x approaches 1. And this is not defined in terms of x equals 1. So it's worth thinking about this in terms of a graph. Like I said, this function approximates our original function. The only time when it doesn't work with our original function is when x equals 1. So that means we can make a graph of the original function by graphing this function, but then we just have to leave a little hole when x is equal to 1. So the graph is going to look something like this. So notice when we look at this, I made a little hole here when x is equal to 1, and that shows that the function is actually, it's undefined at that point. However, if we can still find the limit, because the limit is as the function comes from this side, it's approaching some number, and same thing here, as we're coming from the right going to the left, it's approaching that same value. The problem is we just have a hole at that point. Well, if we want to find that value, we can use this rational function that we were using to draw the graph. Okay, so what we can say is that this limit is going to be equal to the limit as x approaches 1 of this approximating function, x plus 3 over x plus 5. And now at this point, we can do substitution because there's no problem if x is equal to 1. We don't have any issue in the denominator. So if we substitute x equals 1 into there, we get 4 over 6, which is 2/3. So in other words, if the function was defined at this point, the value would be 2/3. However, it's not defined at that point, so all we can say is that the limit as x approaches 1 is equal to 2/3. This is the third situation that we're going to look at when it comes to evaluating limits algebraically. The difference here is that we have a radical expression, so that's going to be key later on. It's a slightly different style of function than what we've had previously. When I look at this function, one thing that pops out to me is that in the denominator there is an x squared. So this would be a problem if x were equal to 0. So one thing that, instead of avoiding the situation, one thing you might be interested in is what is the limit as x approaches 0 of that function. So that's an interesting question that we might ask ourselves. Now, obviously, if we try the substitution method, it's not going to help us very much because when we substitute a 0 in for x, we will get a 0 in the denominator. That's the whole point. So our strategy, our third strategy, is going to be called rationalizing. Now, you might remember this from previous work in algebra. Rationalizing means that we are going to move a radical expression like this one, either from the numerator to the denominator or the denominator to the numerator. And the way we do that is by multiplying by the conjugate of that rational expression. So in this case, the conjugate, we're going to change the minus sign here to a plus sign. Everything else is going to stay the same. So we're going to multiply by that. But again, if we want to keep this expression the same, or keep this function the same, we don't want to just multiply the numerator, we have to multiply the denominator by that term as well. Right, so effectively all of this purple fraction here that I'm multiplying is just 1. I'm not changing anything if I multiply by 1. So we've got a little bit of algebra to do here. Let's see, if you multiply this radical expression by itself, it's squaring a square root. So effectively that cancels out the square root. So this times this would equal just x squared plus 4. If you were to multiply the radical part by positive 2, multiply the negative 2 by this radical part, you would find that those two terms cancel each other out. I'm not actually going to write all of that out. If you don't believe me, feel free to write out the whole thing. But this is really the difference of two squares formula. And then the last two terms we have to multiply out are the minus 2 and the plus 2. So that would equal negative 4. So that's what we get in the numerator. In the denominator, let's see, I don't really want to multiply all of this stuff out, and that'll become clear in a minute why. So I'm just going to write it like x squared times all of this stuff here. Okay. Now, the reason why I didn't want to multiply all this stuff out is because if I look up in the numerator here, I see that there really is just x squared. The plus 4 and the minus 4 cancel each other out. So after we would cancel those, you would find that this x squared would actually cancel with this factor in the bottom that's also x squared. So those two are going to cancel out, and all of this would simplify to that. And what's interesting about this is if we were to now plug in a 0 in for x, we wouldn't get 0 in the denominator anymore. We would get some positive number. So now we can finally evaluate this limit. Now we go back to the substitution method. So we can say the limit as x approaches 0 of our function. I don't really want to write all of this stuff out, so I'm just going to write f of x. Well, that's equal to what we get when we plug in 0 into this formula here. So that would be 1 over 0 plus 4 under the root plus 2. Let's see, so this is 4, square root of 4 is 2, so in the denominator we have 2 plus 2, which means all of that is equal to 1/4, 1/4. And I've got a graph of this function right here. Try to make it not too blurry. You'll notice that as I get the x closer to 0, the y values are getting closer and closer to 0.25, which is 1/4. Now, when I get exactly to x equals 0, you'll notice that there is no y, because the function actually isn't defined at that point. If I keep going a little bit, now we're at numbers that are close to 0.25. Okay, so this is some graphical evidence that the limit as x approaches 0 is 1/4.